Thank you for the introduction. It's really nice to be here and I hope everyone's had a good conference so far. So yeah, my name's Ryan. I've been working with Mark Woolrich for a couple of years now on a new approach to MEG and EEG source reconstruction. And that's what I'll be talking about today, and it's called TASER. So source reconstruction is a really key step in MEG pre-processing and can improve the utility of the data that we measure. But to actually succeed in carrying out source reconstruction, we must first solve something called the ill-posed inverse problem. And this basically arises from the fact that typically we reconstruct thousands of sources from hundreds of sensors. And to do this, we model the source space currents as a linear sum of the sensor level recordings. But to actually derive these reconstruction weights, we have to make some a priori assumptions about the data covariance. And more elaborate source reconstruction techniques take a data-driven approach to this. But for the most part, all of these approaches introduce the sometimes oversimplifying assumption that the covariance itself is actually static in time. But our intuition tells us this can't be the case. We know that the brain is highly dynamic and exhibits changes at the millisecond timescale. So to pivot another way, this is like us watching a movie which is tens or hundreds of minutes long, and then averaging each of the individual frames of the data together to get to representation of that movie. And this isn't wrong per se. This is a valid representation, but it's not the best representation. As you can see here, the average of all of the frames doesn't look anything like any of the individual frames at individual timescales. And this is typically what's happening with MEG source reconstruction, where we collapse in time. So you might now ask, well, if I've got two experimental conditions A and B, can't I just manually segregate these conditions out and construct covariance windows from these different trials? And indeed, you can do this in more simplistic experimental setups, and it's a valid way to proceed. However, this doesn't take into account any neuronal intertrial variability, and it typically makes the assumption that trials are temporally aligned in time in terms of neuronal response. But also it gets problematic when you have complicated experimental setups and you might have more than two conditions, and being able to say specifically when a trial or when a neuronal response takes place becomes hard. And finally, we're still collapsing several hundred milliseconds of data here into one time point and using one or two reconstruction weights. And this problem gets worse when we move to the resting state, where there is no trial structure at all, and it becomes hard to say when an event takes place. But also we've got a complicated paradigm, like someone's watching a movie, drawing the lines then as to when condition A and when condition B is really hard. And sometimes we do have some underlying temporal structure, but it can be hard to manually pluck out when this is, for example, with epilepsy data. And so this is why we make the argument that we need an unsupervised, temporally adaptive approach to MEG and EEG source reconstruction, where an unsupervised algorithm can pluck out interesting segments of time in the data and construct covariance windows from these time points. And this is what TASER attempts to do. And in the TASER algorithm, what we do is we model the time-varying covariance as a weighted linear sum of basis functions. These dynamics, the temporal element of this, are taken into account by these alpha coefficients. And these coefficients are parameterized by a recurrent neural network, which basically learns a mapping from the raw sensor level MEG and EEG recordings to the alpha dynamics. And then the spatial covariance is encoded with these beta basis functions, as shown here by the colored blobs on the brain. And once we've got this estimate for the time-varying covariance, we can then have time-varying reconstruction weights for every time point in our required data. And this is all a very nice idea, but to actually show that it's worthwhile doing, we applied TASER to a pre-existing data set where subjects were sat in an MEG scanner and we're asked to tap their index finger and pinky finger sequentially. And if you don't model the data at all, or you assume that the data is static and you reconstruct this activity, we are not able to distinguish between index finger and pinky finger activations with MEG data. However, if we apply TASER to the algorithm and separate the trials in an unsupervised way, I should stress, between index and pinky finger activation, we are able to distinguish spatially the difference between between index and pinky finger motion in MEG. And so hopefully with that, I've made a somewhat convincing argument that TASER is a tool which we need to employ to really get the best out of MEG and EEG data in an unsupervised fashion in a range of different tasks. And with that, I'd like to say thank you to my friends and collaborators who've been really helpful so far with all of this work, and for you for listening.
Thank you, Ryan. It sounds very interesting. I worked with the source reconstruction in the past, and I remember that the problem is that basically you cannot sometimes trust your results, or you will have these problems where if you want to identify fine differences, it will be kind of hard. So is there any drawback in the method you propose? Of course, this was very brief, but it seems too good to be all true. Not that it's false, but is there something that it's challenging for TASER?
Yeah, so it's a very good question. I should say that the usual rules apply in terms of covariance, estimation, and accuracy when you're trying to be dynamic. So if you don't have enough data points for an event, or if your signal to noise ratio is too low, you will still suffer from the same kind of drawbacks which a conventional beamformer or multiple sparse priors algorithm will suffer from, because you need that data to be there. So that's one thing. And then I guess, as with all source reconstruction algorithms, when you move to real data, there is no ground truth. And so your concern, I guess, will always be there. Yeah.
Thanks. And we have a question from the audience. So it's from Jules Brochard. If you alter the timing in your data, would you risk to confound the cause from a consequence? For instance, the sensory motor perception of your finger.
Sorry, could you repeat the question one more time, please?
Yeah, sure. So if you alter the timing in your data, would you risk to confound a cause from a consequence? For example, the sensory motor perception of your finger rather than the actual finger movement?
So just to clarify, we're not actually altering the timing of our data here when we run TASER. So we don't manipulate the order of events or anything at all. We get a reconstruction weight for every single time point of a data set which we feed in. But to have a stab at the question, which I think is a more general one, yes, if you're not careful, your conception, if you conceive that you're about to tap your finger, that can sometimes confound your results. So you have to be careful with your experimental design and your baseline period. I don't know if that answers the question or not.
We'll see if, Jules, if you want to come on stage or if you want to ask a clarification, feel free to do that. And in the meantime, I wanted to ask you, for applications of TASER to EEG data, would it suffer from the same issue of normal source reconstruction algorithms, where you need to have a decent amount of electrodes, or can you in some way, do you have some advantage over that, and can you afford less electrodes than in the case of classical reconstruction algorithms?
It's a good question. The short answer is I don't know, because I haven't done that investigation yet. But yes, I would suspect that you will suffer from the same kind of classical drawbacks. And to keep, say we had a set number of electrodes, you won't get better data quality. Your signal to noise ratio in your raw recordings won't change. However, the confounds which are introduced by assuming that the covariance is static, you would see an improvement there. So the raw data won't get any better, if that makes sense. But you might glean some extra information by being intelligent with the dynamics of the covariance. But I would have to set up the simulations to give you a concrete answer.
Okay, thanks. And Richard, Etienne, any last question?
Yeah, following up on that last point, it seems like having a method for estimating changes in covariance over time is just a very general and powerful method. And I'm curious if you thought about applying that part of the algorithm to other data. For instance, I mean, I'll be talking later a little bit about whitening voltage data from electrophysiological recordings and how that kind of helped us. But that, you know, a core problem of that is getting a good estimate of a covariance matrix, which I usually assume is static, which I know is not a good assumption. So have you thought about applying that part of the toolbox to other data?
To be completely honest, it's kind of happened the other way around. So my supervisor, Mark Woolrich, and his students in the past have really kind of cut their teeth in modeling covariance and time-varying covariance with a thing called a hidden Markov model. And I would agree with you that it's a kind of more general problem to solve is modeling this covariance. It just so happens that source reconstruction, when you take a data-driven approach, is all about the data covariance. So it's a really nice natural application of these modelings of covariance. Very good question.
Okay, and if there are no further questions from the panelists or the participants, we can move to our next speakers. Thanks again, Ryan. And